All right, so we are starting today by taking a look at some other concepts that are related to chemical reactions and chemical equations. So if you did the chapter 7 pre-lecture, if you watched those videos, you know that I talked in that video about 5 different types of chemical reactions. The combination reaction, where we take multiple reactants and they fuse together to make a single product. We talked about the decomposition reaction, where we've got a larger molecule that breaks down into smaller molecules. We talked about replacement reactions, where we usually have ionic compounds that are switching ions. And then we have combustion reactions, where things react with oxygen and get set on fire. Now, in addition to all of those, and if you haven't done the pre-lecture video series yet, again, I'd encourage you to look at it and look at that pre-lecture activity, because one of the things that will really help with balancing equations is that there is some pattern recognition that can go in. And in particular, what I would look at is replacement reactions. Replacement reactions are very big on patterns, because what we'll see in replacement reactions is that those ions don't change. They just switch. And so since the ions don't change and they just switch, it makes balancing a lot easier, because I don't have to worry about the individual atoms. I can worry about the ions themselves. There are a couple of other things that we would want to look at, though. And they got cut off here. I'm not sure why. So the other kinds of reactions that we would want to look at in particular are the acid-base reactions, the gas-forming reactions, and the redox reactions. Now, acid base and gas forming, for those of you that have done the readings already, those are going to look like double replacement. Basically, we're just talking about more specific classes of double replacement reactions. On the redox front, what we're going to see is that redox reactions are a kind of an umbrella term. And as an umbrella term, what we're going to see is that most of the other types of reactions that exist fall into this big, larger category of redox reaction. And so it becomes just a matter of recognizing some of the key attributes of redox. And we'll talk about what those key attributes actually are. So let's take a look at each of these piecewise here. Acid-base reactions are double replacement reactions. Now, what do I mean by double replacement reaction? So again, what we're looking for specifically is a recognition that I can look at each of these reactants and see individual ions. Now, what makes a replacement reaction is that we are essentially going to see partner swapping here. So easiest way to look at that is if I just take the two things that have positive charges and flip-flop them, that becomes the basis of my two new compounds. So that's what a double replacement reaction ultimately is. I have two ionic compounds, and I just took the two cations, the two positive charges, and I switched them to make two new compounds. So When I do that, that means that the sodium now is with the chlorine. So that's how I get the sodium chloride, Na plus and Cl minus makes sodium chloride. Where does the water come from? Well, the hydrogen ion is with the hydroxide ion. H plus, OH minus, that's now H2O. So with acid-base reactions, we are always going to see this kind of a pattern. Water is going to be one of the products because the hydrogen from the acid and the hydroxide from the base are basically going to neutralize each other, cancel each other out, and the net result of that is water. And then the other product is just going to be what's left over from the acid and the base. So in this case, it was chloride from the acid, sodium ion from the base. Put those two together, it's sodium chloride. It's always going to be a salt. Remember, salts are just ionic compounds. So any ionic compound fits this particular category and description. Going back to the concept of balancing here, why is it important to think about these things in terms of ions instead of just elements? Well, if I can recognize that my ions are not changing, it becomes a lot easier to keep track of them. So I can see that I have one sodium ion on each side. I have one hydroxide ion on each side. I have one hydrogen ion on each side. I got one chloride ion on each side. And so since everything is already balanced ionically, I know I don't have to manipulate this equation. It's already balanced. So I don't have to add any 2s or 3s or anything else in here because everything's already taken care of. Now, this is a simple example, but when we get to more complex examples of double replacement, what we'll see is that that kind of mentality makes it a lot easier to see what needs balancing. So if I can recognize, oh, wait, I got 2 hydroxides over here and only 1 over here, I know I need to put a 3 in front of that compound to give me the 3 hydroxides that I need. All right, so here are some common acids and bases. So we've seen a number of these just kind of in different places and experiences. Most of the acids are acids that we encounter in the laboratory. So hydrochloric acid, nitric acid, sulfuric acid, acetic acid. These are common laboratory acids. In the case of hydrochloric acid and acetic acid, they also find their way into some common household products. So acetic acid is the ingredient in vinegar that gives it its smell and its taste. So most vinegar is about 5% acetic acid and 95% water. Hydrochloric acid, on the other hand, is found in certain brands of toilet bowl cleaner, where the acid is used to break down the different parts of the toilet, and it's still plumbing safe. On the base side, sodium hydroxide, we're gonna find hydroxides all over the bases side. Sodium hydroxide, also known as lye, is found in a number of different products. Most commonly, it is found in drain openers. You combine sodium hydroxide with bleach, and you've got drain, basically. And so what happens is that those two components work together to break down the organic stuff that gets caught in your sinks, that gets caught in your drain pipes and causes them to back up or become slow. Lithium hydroxide, find that more often with lithium ion batteries. Potassium hydroxide is also known as potash. Calcium hydroxide is called lime. Barium hydroxide is another common base as well, although less and less common because of some of the toxicity around barium. Really only find barium being used commercially in medical applications. Barium, radioactive versions of barium are good for radioactive imaging in some cases. So just depending on what kinds of things are being done. The second type of reaction that we want to take a closer look at is the gas evolution reaction. So this is a double replacement reaction as well. But instead of getting water, what we're going to get instead is some kind of a gaseous product. Now, depending upon the circumstances, depending upon what is being reacted, sometimes the gaseous product is actually the result of a secondary reaction that takes place when the primary product decomposes. And so a good example of that is when we see a double replacement reaction that generates carbonic acid, H2CO3, what happens is that carbonic acid breaks down and we end up getting carbon dioxide and water forming at the same time. And we see similar kinds of things happening when we have sulfurous acid. We'll get sulfur dioxide and water as byproducts, or ammonium hydroxide will break down into ammonia and water. And so when we see balanced chemical equations, when we're trying to predict products, using those 5 types of equations as kind of a guide, this is one of those things that we kind of have perking along in the background, especially when we see these usually are the result of acids interacting with some kind of a salt that we don't immediately recognize as a base. It's not a hydroxide. The third type of reaction that we want to take a closer look at today are the redox reactions. Redox reactions are those that involve the transfer of electrons. And what we really want to pull out of redox reactions is that this is not a single type of reaction. So for the other 2 types of reactions, we looked at them and said, okay, well, they're double replacement, and maybe there's a little bit of decomposition shenanigans going on with the gas forming reactions, but for the most part, they're double replacement. And we can just look at the ions, see the ions switching around, and kind of know what's going on. Redox reactions kind of fit into that category of everything else. All the other types of reactions that were discussed in the pre-lecture, that were found in the early readings, they all have this kind of characteristic in common. They all involve the movement of electrons. So the question becomes, how do I identify these kinds of reactions? What do I need to look for? Well, if I can identify any of those 4 categories, I know it's redox automatically. But what if it's not one of those 4 categories? What are some things that we can look for? Well, there are a couple of things that we could try to get into. We can start to try to look for charges. By definition, oxidation is the loss of electrons. By definition, reduction is the gain of electrons. So we can start to look at the charges of things and see if the charges are changing. And that would be a really good sign that a redox reaction is occurring. If I start with iron 2+ in some kind of a compound, and I end up with iron 3+ as a result of the chemical reaction, I can look at that and say, hey, wait, the charge changed. Charge change means we had an electron move. This must be redox. Now, in terms of keeping oxidation and reduction straight, there are a couple of ways of going about it. The first is a mnemonic device. It's called oil rig. Oil rig stands for oxidation is loss. So that's the oil. Rig would be the reduction is gain. Now, if that one's easy enough to remember, go ahead, use it. There is a second mnemonic that has some popularity. It's actually the one I was taught how to use when I was an introductory chemistry student, also many years ago. And it goes like this. Leoger. Leo, the loss of electrons is oxidation. Ger, the gain of electrons is reduction. Leo the lion goes grrr! I was like breaking the sound barrier with that one, just to see who's still up. But both of these processes happen at the same time. So you can't just have oxidation, you can't just have reduction. You can't just have oil, you have to have the rig. You can't just have Leo, you have to have the GER. Both processes have to be there. So if I can't immediately see from charges that something is changing, what are some other things that I can look for? Well, some telltale signs are here at the bottom. If I see that a substance is reacting with elemental oxygen, so I have anything plus oxygen, I know I'm getting a redox reaction. Now, I should be able to recognize that it's going to be one of two processes. It's either going to be a combustion reaction, where I've got some sort of hydrocarbon reacting with oxygen to make carbon dioxide and water, or usually it's a synthesis, a combination reaction where like a metal and oxygen come together to make a metallic oxide, or sulfur and oxygen come together to make sulfur dioxide, or something along those lines. So again, if I can kind of come back to my 5 classes, reacting with oxygen is either combustion or a combination. But if I don't recognize those for what they are, I can just look at it simply and say, oh, it's reacting with oxygen, it's got to be redox. Another example is when we have metals reacting with non-metals. This is another example of a combination reaction. If I have sodium reacting with fluorine to make sodium chloride, I started with no charges on the elements. Now I have ions. That's the basis for my redox. But again, ways to look at it. Can I see that charges are moving? Can I see that the charges that I start with are not the charges that I'm ending with? That's a real key factor. That's ultimately going to help us figure out whether or not we've got redox going on. So full disclosure here, I could not find a great way to get these to be paired deck questions. I still want you to get the participation points. So go ahead and enter in Redox so that you get that participation point along the way here. But we're going to do this together. So the question is this reaction, we'll start from the top, is this reaction a redox reaction? So I kind of go through the checklist. Do I have anything reacting with elemental oxygen in the first one? No. Do I have a metal reacting with a non-metal in the first one? No. Do I have evidence of charges changing? Yeah. I go from zinc. Zinc has no charge here. The zinc has a +2 charge. Copper has a +2 charge here. It has no charge here. So I can clearly see that the charges are changing. So is it redox? Absolutely. This is a redox reaction. The question is, what was oxidized and what was reduced? Here's where we need the over or oil ring. If something loses electrons, what happens to its charge? Is it going to go up or is it going to go down? It's going to go up. Loss of electrons means we're going to get more positive. Positive numbers are bigger than negative numbers. So which of those two reactants got more positive? The zinc. The zinc got more positive. The zinc was oxidized. Oxidation is loss of electrons. So the zinc lost electrons. It got more positive. The copper, on the other hand, got more negative. It went from +2 down to 0. So we would say that the copper, in particular, if we were being very specific, the copper 2+ was the thing that gained electrons, was the thing that got reduced. All right, let's take a look at the second one. Let's go through the checklist. Is there something reacting with elemental oxygen here? Yeah, we've got iron reacting with elemental oxygen. This is redox. So now we have to get into what is being oxidized, what is being reduced. So it's going to be hard to do that without thinking about charges. Luckily, we have some charges that we should know. What charge does oxygen take when it makes ionic compounds? What does the periodic table tell us? Yeah. It's in group 16. Everything in group 16 has a -2 charge. So oxygen, we would expect -2. So it went from 0 charge to now it's -2. Its charge went down. That's reduction. So what got reduced? The oxygen got reduced. By process of elimination, we could conclude that the iron got oxidized. Now, how do we prove that to ourselves? Well, we can look at this and go, well, metals make positive ions. If we did the reverse crisscross here, the subscript of 3 would become the charge of the iron. The subscript of 2 to charge the oxygen. So the iron's +3, so it went from no charge to +3 charge. So it had to lose electrons to do that. All right, last one here. All right, this one's kind of tough. What we have to think about is if I've got -2 charges from the oxygen here, I should be able to see that the zinc went from a 0 charge to a +2 charge. And so the zinc again is getting oxidized, which means that the manganese 4 oxide got reduced. This last one's kind of a tough example. It's not as easy or as clear cut as the other ones. Now I'll tell you, for the kinds of problems that you're going to get in the future, it's going to be much more like these first two than the last. But the things to kind of look for, if I see an element turn into a compound, I know redox is at play. Because you can't go from element to compound and not have some kind of change in charge. And if you go from compound to element, same thing. You went from something that was charged to something that isn't charged anymore. So we're not going to get all the way through electrolytes for today, but electrolytes fit into the solubility category that we're going to talk about on Friday. So it's okay. They still go together. Before we get to that spot though, I want to talk a little bit about solubility vocabulary because it is important to the next kind of discussion. So when we talk about solubility, we're talking about the ability of one substance to dissolve in another. And so the term soluble just literally means it can dissolve. So for the most part, we're going to talk about things called aqueous solutions. Aqueous solutions are solutions that water is the primary component of. So if I have something dissolving in water, the resulting mixture is an aqueous solution. Aqueous literally means water. So a water solution. Water being the thing that does all of the dissolving. And so if we think about things in terms of their ability to dissolve in water, we can come up with two different terms. Things that dissolve in water are considered to be soluble in water. Things that don't dissolve in water would be considered insoluble in water. And where we're going on Friday is we're talking about a particular class of solubility. We're talking about something called an electrolyte. Now, you're familiar, at least in concept, with electrolytes, thanks to things like Gatorade and Powerade and other kinds of sports drinks. The term gets thrown around a ton. But what does it actually mean? Well, by definition, an electrolyte is a solution that is able to conduct electricity. How does it conduct electricity? Well, it conducts electricity based on the presence of ions in the solution. The more ions that are in the solution, the better it is at conducting electricity. And so we can split electrolytes into three categories based on the number of ions that are in the solution. The strong electrolytes, those are the ones that conduct electricity well. They have lots of ions in solution. The weak electrolytes can conduct electricity, although they do it kind of poorly. And so they have ions in the solution, but not nearly as many. And then the non-electrolytes, the ones that don't conduct electricity at all, well, as you'd expect, they don't have ions in the solution at all, period. So we'll leave it at that for today. Go ahead and get that last participation point before you leave.